All right, for the heat treatment here, control heating and cooling to bring out desired change in metal and alloy. Objective, microstructure change, improve mechanical properties, i.e. toughness, measurability, strength, reduce residual stress level. So for heat treatment, we have global. Global means the whole material we do heat treatment, or local means only small part of the material, all right? It's not the whole material. For the joint like welding, so we do heat treatment for the joint area only. So that become local. So here they talk about heat treatment can be localized or maybe the whole material. Like a small specimen, they can use furnace, gas fire, electric. Localized can be localized heat source by using flame, induction, or laser heating, and to control the temperature used, thermocouple, yeah, optical parameters. So here they talk about furnace and oven. We can use gas fire, electric furnace. All right, so this one you need to memorize a bit about the heat treatment cycle. So in heat treatment cycle, always you got heating rate, soaking and cooling. And from here, we have control, they call it control. And here is uncontrol. So they start to control. Normally we talk about PWHT. Control start from 300 degrees C up to 600 degrees C or maybe 650 degrees. So this is control. This is 300, right? This is 300. From 300, control up to 600, control, and then when cooling, they control up to 300. Then after 300 degrees C or below 300 degrees C, this is uncontrolled. The same thing goes here. Before 300 degrees C is uncontrolled, but after 300 degrees C, they start to control the time and the temperature. Must be not more than, according to TWS spec, maximum 220 degrees C per hour. Okay? All right. So type of heat treatment, here we have many heat treatment here, but remember, in this heat treatment, we have what they call it upper critical point, or they call it also upper critical temperature, which is from 880 degrees C up to 920 degrees C. Only three processes here, which is annealing, and then normalizing and quenching. And quenching. All right. Then we have another critical point, which is must be lower than 723 degrees C. They call it lower critical point or lower critical temperature. So all these, recovery and recrystallization, must be under here. Stress relief must be here. Tempering must be here. And you write down again under preheat. Write down preheat. And also PWHT. precipitation hardening. All this must be lower critical point. Please memorize this. So remember, for this topic, heat treatment, CSWIP, we got two critical points. One is upper critical, another one is lower critical. And remember, memorize, upper critical, 3 process, annealing, normalizing, and quenching. The other process, always at lower critical point, which is preheat, PWST, recovery, recrystallization, tempering, precipitation hardening, stress release, hydrogen release, all those carried out at lower critical point. Please memorize all this with the temperature. Okay, memorize. When it comes to upper critical, 3 process, annealing, normalizing, quenching, that's it. Other process, lower critical temperature. Yeah? And other things need to remember is when it comes to quenching, quenching must be followed by tempering. Tempering coupled with quenching. Tempering not for other process. When it comes to quenching, always tempering. Memorize. Okay? All right. This thing you must memorize. Yeah? Which one is upper critical? Which process upper critical? Which process is lower critical? Right? Memorize them all. All right, you move. So here, they say annealing and normalizing, phase change to austenite. What we could understand from this statement, phase we can assume as grain structure. All right, when we heat material more around 900 degrees C, we got austenite grain. Austenite grain means large grain. All right, produce large grain. Because when we heat the material, it start to expand. When it start to expand, it will produce large grain. Yeah, so that's why it said here, phase change to austenite, meaning the grain structure now expand, become large, and then they call it austenite. Other process all carried out at lower critical. Example here, they put 7 to 7, like recrystallization, stress relief, PWST, all other process must be at lower critical. Yeah? Right here, recovery and recrystallization, stress relief, and post-well heat treatment, he said no pace, not changing grain structure. They're not changing to be austenite. Yeah? All right, in full annealing here, still, heated to high temperature. High temperature here, we refer to roughly about 880 degrees C up to 920 degrees C, where we call it upper critical temperature or upper critical point. Cold for some time and then slow cold. This is very slow cooling, right? Basically, from 900 degrees C, they will, normally from 900 degrees C, they will reduce temperature in furnace up to 600 degrees C before they slow cool in air, right? So this is control in furnace, the temperature. So this is very, very slow cooling rate. What happened? It will produce coarse grain size. When it produces coarse grain size, normally it will produce low toughness. Write down low toughness. So it said coarse grain here. You can see that the white color ferrite and the black color perlite, this size is big, large coarse grain. You see here? Comparing to this one, all small. This is under normalizing, all small grain. Here we got large grain. Yeah? All right, normalizing. Again, they heat up to 880 degrees C up to 920 degrees C. This is under upper critical temperature. Still heated just to where austenite is stable. Air cooling, fairly rapid compared to annealing. It's quite fast. After 900 degrees C, take out material from furnace and let it cool in air cool. All right. So it produces grain refinement, smaller grain here, and then as a result, you got high toughness. Yeah. Compared to this one, coarse grain, you got low toughness. Here, grain refinement, more smaller grain, you got higher toughness. Okay. All right, recovery and recrystallization is said here. This apply for cold work, like bending, forging, okay, hammering, when the material is still cold. So what happened here? It will increase strength but reduce ductility and toughness. So how to rectify this problem with the grain, with the properties? So it said reverse by recovery and recrystallization. Rearrange the grain structure. So recovery reduce store energy in cold work or deform, dislocation move, align at heat treatment, new defect-free grain nucleate from grain boundaries and grow. For example here, this grain structure we got during cold work. When we heat, this is the temperature, all right? When we start heating it, increase the temperature, so we can see that now the grain structure change to a new grain. So this is what they call recrystallization. Yeah. Okay. All right, quenching. Quenching again, this apply in 910 degree, which is upper critical temperature. Then we got austenite. And then this is very fast cooling. You see here the time, very fast. So as a result, we got martensite grain. So martensite grain here, which produce hard and brittle. Hard and brittle material, martensite. Okay? That's what we got in quenching. Then, because we got hard and brittle material after quenching, so it must always follow by tempering. Yeah. All right. So here, heating to annealing. Annealing here meaning they are referred to temperature around 900 degrees C. Fast cooling using brine, water, or oil. But it said here it will decrease ductility and toughness, and normally followed by tempering. So remember, tempering always coupled with quenching. So this tempering they carried out at lower temperature, meaning that at lower critical point or lower critical temperature, less than 700 degrees C, which is less than 700 degrees C. Yeah? To tailor the hardness and strength of martensite, which is produced by quenching. So that's the purpose of tempering. Perform after quenching to reduce brittleness, ductility, and toughness are improved. Remove stress during quenching. So this is what happened when we have quenching here, water quench. So it produces 380 hardness weakest, but tempering at 700 degrees C, then it will reduce the hardness to 245, right? All right, here stress relief, the purpose is carried out at lower temperature to reduce residual stress. So lower temperature here, this must be lower than lower critical temperature, which is less than 7 to 7 degrees C or 7 to 3 degrees C. So tempering here carried out after quenching. Okay. All right, stress release and PWST. Remember, tempering, stress release, all those carried out at lower 7 to 7 or 7 to 3 degrees C. So here it said no phase transformation. So meaning at this point, there is no austenite. Slow heating and cooling, soaking time 1 hour, depend on the thickness. If you got 2-inch, then 2 hours. Yeah? And highlight this one, the temperature for PWST, 550 to 650, highlight this. Stress relief carried out after cold work or welding at lower temperature, which is at lower critical temperature or lower critical point. And this one we have talked yesterday in the stress and distortion. So again, we have heating, we have soaking, and then we have cooling. Okay. So here we got residual stress goes down at soaking time, it goes down at lowest level. So again, after cooling, then it's at lower level. But for the yeast strain, it goes down during heating at lowest level during soaking, but it will increase during cooling. So please memorize a bit about the things here. All right, what happened during heating, what happened during soaking, and what happened during cooling for yeast strain and residual stress. Okay, memorize a bit. All right, this is what doing PWST recommendation here is to provide adequate support, control heating rate over uneven expansion, control soaking, control temperature, control furnace, control cooling rate. Yeah. All right. You are assigned to a heat treatment company to witness the heat treatment being conducted. The heat treatment are being conducted on various products for major offshore oil and gas project that you have been involved with. All right, question 1. This one refer to spec. Question 2. I think you may refer to spec this one. 3, very clear. Spec 4, spec 5, spec 6. This one is no spec. 7, mentioned here, spec. 8, spec. 9, no spec. 10, spec. All right, I repeat again. Question 10, spec. 9, no spec. 8, spec. 7, spec. 6, no spec. 5, spec. 4, spec. 3, spec. 2, spec. 1, spec. All right. All right. Look at question number 1. While inspecting some cast duplet valve body, one of your inspector asks if the casting require heat treatment process, which of the following will most likely be applied to those items? Right, so the question asks about cast duplex. Right, get the spec 14.2. And the material detail for the stainless and duplex stainless steel, 14.2 material details. All austenite stainless for verification welding shall be grade 316. Then it said here, all stainless steel shall be supplied in solution anneal. And then for duplex stainless, what is said here, all duplex stainless shall supply in solution annealing condition, right? So that will give us answer of A, solution annealing. So basically, what is it, solution annealing? Solution annealing is talking about the heat material, for example, this stainless steel or duplex stainless, heat to 1100 degrees C, then quench. Then quenching carried out, meaning you need to put this material inside water or oil, quenching, very fast cooling, in order to dissolve carbon. So that's the purpose of having this, they call it solution annealing. Heat material up to 1100, which is above upper critical temperature, quenching in water or oil, and then the purpose is to remove, or they call it dissolve carbon. Question number 2, this question asks about a set of fabricated bracket manufacturer from 316 stainless about to be heat treated. Which of the following apply? So the question asks about stainless steel, 316. The set of fabricated bracket manufacturer from about to heat treated. So they already, this one they talk about maybe there is something made of stainless steel already welded. Now they say they're going to do heat treatment after the weld. So that's the question asked. Yeah, about to heat treated here after welding. So that's the question asked, right? Now look at 14.4. In 14.4 on the, you can see the statement here. Post-wear heat treatment are generally not necessary for both austenite and duplex stainless. Heat treatment, however, may be required for the purpose of stress relieving after extensive cold working, cold deformation, etc. This heat treatment may only be carried out if approved by company maximum temperature 450. So that statement will give us the answer of Bravo. Yeah? Post-weld heat treatment isn't generally conducted on this type of material. Number 3. All right, during post-weld heat treatment of small welded fabrication, you observe heat treatment personnel applying heat by heating torch. In accordance with CSWIP spec, do you consider this an acceptable practice? So this guy applied heat treatment by using torch. Right, now look at your spec 19.1, section 19.1. And the post-weld heat treatment here. All right, general. All PWHT treatment shall be carried out in controlled manner either by the use of furnace or as an alternative by the use of heating blanket. So they only ask for furnace and heating blanket. When PWHT to be carried out by the use of furnace, the component shall be placed centrally. All right, so there is 2 choices here to do the heat treatment, furnace, heating blanket. So there is no, they not mention anything about heating torch. All right. So if you look at the answer for number 3, the answer goes to C. No, this application method isn't acceptable because it's not mentioned in the spec. The answer A is wrong because it said yes. B also wrong because it said yes. Okay? Basically, it's not mentioned in the spec. All right, look at number 4.
Pak Hasan.
Yeah?
How about for preheat? Can we use the torch
Right.
or preheat?
Yeah, but
Can we use the heating?
that's for preheat is different. The
Can we
question
use the
here
torch?
asking about post-well heat treatment. But if you want to use heating torch or something for preheat, you need to check from WPS. In real life, check from WPS.
Oh.
But in these questions, they ask for post-well heat treatment, PWHT.
Yeah.
For post-well heat treatment, from our spec, it mentioned only 2 choices, by using furnace or maybe using heating blanket. Yeah?
Blanket.
Okay? All right.
Yeah.
Number 4, unfortunately, the stress relieving of the welded fabricated steel structure hasn't been witnessed by any of your inspector. When you review the post-weld chart, you notice only 2 thermocouple have been used. In accordance with TWS spec, do you consider this to be acceptable? All right, look at the same page. Now look at 19.2. All right, temperature measurement. All temperature measurements shall be monitored by the use of thermocouple and multi-point temperature recorder. A minimum of 3 thermocouples shall be used and placed in such a way to ensure uniform heating throughout the component. No thermocouple reading shall be more than 30 degrees apart throughout PWST heating cycle. All measuring device being used shall have valid certificate of calibration. All calibration certificates shall be checked by company inspector before post-wear treatment process carried out. All temperature recorders shall be checked by company inspector to ensure the speed of chart being used match with the temperature recorder. So here they mention about minimum 3 thermocouples. Right. So that will give us the answer of D. No, a minimum 3 thermocouples shall be used and calibration certificate required taken prior to heat treatment process. Why the answer A is wrong? No, all post-wear heat treatment shall be witnessed and minimum of 3 thermocouples shall be used. B, yes, only post-wear heat treatment chart required reviewing by inspector. C, no, all post-wear shall be witnessed. An inspector has to be present 100% of time throughout the post-wear heat treatment process.
Yes.
So as an inspector, basically when you go and visit, check the procedure, check the equipment use, check the calibration certificate. When everything's there, then you're not always waiting there. If the heat treatment, from start to the end, maybe take, 5-6 hours, it's not necessary for you to always there. For the starting point, you always go and check equipment, everything's there, and then you off. From time to time, you go and check again. It's not always 100% as expected to be in the heat treatment process there. Yeah. Right. If we check everything's okay, then no need to be there all the time. Yeah. So I think D is the best answer. It follow what statement in the specification. Number 5, it is requirement for quench and temper component undergo heat treatment. One of your inspector asks you what is the maximum temperature required for this material. Which of the following is correct according to CWI spec. All right, look at 19.3. So they are talking about quench and temper, QNT, and doing this PWST. Yeah. All right, 19.3. This is talking about the heating, cooling rate, soaking time for different material. So what we can see here, there is three material they mention in this 19.3: carbon manganese, quench temper, all right, and austenite duplex stainless. Hello, Marvin. Welcome back. All right. So Marwan, I will give to you the question number 1, 2, 3, 4. I think now we are discussing question number. Now we're discussing question number. Let me check.
6.
Question number 5. Yeah. Okay. Question number 5 now. But I will give you the answer after this. 1, 2, 3, 4. Okay. All right. Look at carbon manganese. Maximum post-wear treatment 650. All right. Minimum post-wear temperature 580. Metal thickness more than 25 mm or 1 inch. Soaking time 1 hour. Heating rate above 320 degrees C. Control heating. And it must be 5,000 divided by thickness, no longer than 220 degrees C per hour. Cooling rate shall be the same as the heating rate. All right, look at quench and temper. When required, PWST shall be the same, all right, but shall not exceed 600. The difference with here is 650 for carbon manganese. Quench temper say 600. Heating rate shall be controlled from 300. Cooling rate shall be controlled to 300. So a bit different from carbon manganese because carbon manganese asking for 320. All right, 320. Quench 300. Insulation and thermocouple shall not be removed until component temperatures drop below 110 degrees C. In all cases, thermocouple and insulation should not be removed until component temperatures drop below 100 degrees C. That is on the note. All right. We check from the question and answer here. All right. We know that quench and temper maximum temperature is 600 degrees C. Carbon manganese 650 degrees C maximum. So A is not the answer because it's not really the same in terms of maximum temperature. B, you will never permit post-wear achievement to carry it out of this method. So this is totally wrong. C, the TWI spec doesn't reference this information, but I expect to be around 680. So that is totally wrong. We already know in the spec maximum 600. So that's why C is also wrong. Then the best answer goes to delta. Okay? All right, 6. During post-wear heat treatment, what sequence of events occur to the properties of the material? Right. So this question basically refers to this one. All right, we have heating, soaking, and cooling. So what we can see from here, both residual stress and yield strength at the highest position. During heating, both goes down. During soaking, both at lower level. During cooling, residual stress still at lowest level, but yield strength now goes up. So you can see the difference here. During cooling, one goes up, one still maintained down, right, at the lowest position. Okay? All right, so that will give us the answer of here, C. Yield strength decrease, stress decrease, yes. All right, that occurred during. So we know that we have heating, soaking. So both are lower, goes down, and then goes up there. Another one goes down and stay like that. So here, yield strength and stress lower, then during cooling, yield strength increase. That's correct. Okay. A is wrong because you say yield strength increase. Wrong. It's never increase. From starting, it's never increase. Stress decrease, yes. Yield strength decrease, wrong. Yeah. B also wrong, and also do for D also wrong. Yeah. Marvin, I remember you didn't have the answer yet with you. Marvin, I'll show you question number 1, 2, 3. Get the answer. Question number 1 is A. All right. 2, Bravo. 3, Charlie. 4, Delta. 5, Delta. 6, Charlie. 7, oops, we don't discuss yet. All right, 7. All right, guys, look at question number 7. After post-well heat treatment process has been carried out on the same thick to thin pipe spool, thickness ½ inch to 1 inch, you notice the heating rate is recorded 200 degrees C per hour. That's for carbon manganese. In accordance with CSWIP spec, is it correct? All right, look at the same page, 19.3 section. 19.3. What we can see here is a heating rate above 320 degrees C control heating. The heating rate shall be 5,000 degrees C divided by maximum metal thickness, but not greater than 220 degrees C per hour. All right, guys, do you have calculator with you? How about you get 5,000 divided by 25? What is the
200.
5,000 divided 25?
200.
Yeah, Pak Ashari?
200 degree.
We got 200. We got 200, right? If the thickness is 2 inch, so we divide by 50. What's the answer? 100. Okay. The thing is like this. In PWHT, we have right? We have temperature here. And then we have time. Time is here, okay? So this is heating. This is cooling, soaking. And this is cooling. So what happened here is, say, here, at this point, to this point, (300° C). And let's say that maximum we have 600 or 650° C here. And the same goes to here. So this area, they call it control. And this area they call uncontrolled. So here, when the heat goes up, before 300, there is no control, no need to worry, doesn't matter. But when it comes to 300° C above here, so this is what they want, what we got here, example, 5,000° C divided by the thickness. Example, we have 25 mm. Then we got, what is it, 500 here, we got 200° C per hour required here, at this point. So at this point, they not allow the temperature per hour more than 200° C at this point. Above 300° C, then we must refer to, we must look at this, yeah? Yeah. So that's the point here. So they ask at this point 200° C per hour, at this point, above 300. Yeah, got it? Okay. So we understand that 200° C per hour here, when we have 5,000, example, we're using thickness 25 mm example. They said here 5,000 degrees C divided by thickness 25 mm. Then we got roughly about 200° C per hour. Yeah, degree C per hour. So, but what in our spec mentioned maximum.
220.
In our spec mentioned not greater than, meaning maximum is 220° C. Yeah, so that is what they want. So back to this one. In spec mentioned maximum allowed 220° C per hour. Yeah. So in this case, 200° C, that's still acceptable because it's not more than 220. So the answer goes to C, yes. A is wrong because it said minimum, where it must be maximum. No, it should be 40 degrees C per hour. That's the wrong statement. D, yes, providing cooling rate is 220° C per hour. If you got 200° C, then Cooling rate also the same, because it's based on the thickness. Yeah? All right, 8. While reviewing heat treatment chart for post-vacuum process, you notice the temperature is not recorded below 350 degrees C on the cooling cycle. All right, look at the 19.3. Sorry. All right, here it's very clear, mentioned in the spec. In all cases, thermocouple and insulation shall not be removed until component temperature drop below 110 degrees C. So back to questions. All right, the best answer goes to Charlie, because it's very clear mentioned here, 110. Yeah. 9. In certain cases, heat treatment are conducted on cold work components, such as cold roll steel plate. Which of the following heat treatment would you accept? Would you expect conduct on this component? All right. Back to our handout note here. Stress relief carried out after cold work. Yeah? So that is in your note. So that's why the answer is alpha. Agree with that? All right, last questions. You notice from your record, you don't have an inspection report for component that has undergone PWST. In this case, what would your course of action be? All right, look at 19.4 here. In 19.4, it said, all post-well charts shall be reviewed by all parties, company, contractor, and where applicable, third-party QC. The post-well chart shall be filed in contractor's QA/QC department and shall be made available for review at any time. And note, full inspection carried out, conducted in accordance with initial inspection requirement of the system. All right, that will give us the answer of Charlie. It is requirement that all components undergo full inspection after post-vacuum process has been conducted. In this case, it will not be acceptable, because here it said you don't have inspection report. Maybe inspection report gone missing. Yeah.